Oh, 6.4 work. Briefly about this, work is force times distance. The force is basically the force applied to an object times the distance traveled by the object. And what we have here is a table of values or units, good to be familiar with, to know that the force we use pounds for the US units, for European units we use newtons, for distance we use feet or inches or miles, for SI units we use cm, meters, km. Then the work, because it's force times distance, it would go pound feet or pound inches. The same thing, newtons, centimeters, newtons, meters. And this example was a quick example where they give you the force and they give you the distance. They ask you to find the work. And this was the next one. They said this mountain climber is about to haul up a 50-meter length of hanging rope. So what is that 50 meter? That's a distance. You can tell from the unit. How much work will it take if the rope weighs 0.634 newtons meters? So newtons meters, what is that? That's what we need here to find the work. What do we need? We need force and distance. I'm not sure how many remember what force is. Force in physics, it's so the work, again, this is work. It's weight times distance times the other distance. So what we do here is, first we can find the force, which is force times distance, and the weight here, newtons per meter, that's for the weight. This is the weight, and it's given to us, its weight. So then notice how the meters cancel. If we multiply 0.634 by 50, that will give us 31.7 newtons. As soon as we found the force, we can find the work. So then the work being applied here is force times distance. The force is the one we just found, 31.7 times the 50 meters. And since it's in newtons and meters, so this is in newtons, that's meters, we get the 1585 joules. So far, students say, wait, what, everything we're doing physics, what is this, physics or math? Well, we're assuming that the force being applied here, it's always constant throughout the object. So it's not throughout your work. While you're pushing this object, you are applying a constant force. Okay, so if you go back to the main definition up here, we said constant force on the second line. This is a constant force. So here, how about if we're asked to find the work done by variable force? So every time you're pushing the object, you're not applying the same force over a certain distance, and that's where calculus kicks in. So we say if an object is moved along straight line by a continuously varying force, is changing force, f of x, then the work done on the object from x equal a to x equals b is adding up all these forces, f of xi delta x, where limit goes to infinity as we did in Calc 1, or in other words, is going to be the integral from a to b, because you're traveling on an object from a to b. So the object was here, then here, then here, but you're applying different forces. To sum up all these forces, you go the integral from a to b, f of x dx. And this is an example to that. So here we have the work is the integral from 1 to 3. They tell us from 1 to 3 f of x, and f of x they give it to us, x squared plus 6x, and I'm sure everyone can integrate that. Don't forget it's feet pound. They give us the distance feet. They didn't say anything about the unit for the force, but you can assume it's pound if it's not given. So next we introduce what we call Hooke's law, a physics concept. Hooke's law said that the force, call it F, required to compress or stretch a spring is proportional or directly proportional to the distance that the spring is compressed or stretched from its original length. So if you have a spring you put on the table, that's its original length. When you apply the force to it, like to stretch it or compress it, then this is saying then the force that you are required to compress it or stretch it is always proportional. What does that mean, proportion? Proportion means the force is a constant times the distance traveled. So we can rewrite it like so, that f of x, the force, is k is a spring constant, times x, but we need it to be bigger than 0 here. So this is what we have, an example. So here what we have, this is the original length of the, from here to here of the spring. We stretch it out from A to B, like it went from here to here, that's A, and then to B. So notice we need to convert the centimeters to meters by dividing by 100. To convert from cm to meters, divide by 100. So the 8 becomes 0.08. And then what is A here? A is, so remember how it was original was 0.08. And then it was stretched by 14 centimeters, so by 0.14. So we say to find the bounds A and B, we go A is going to be 0.014 minus 0.08. So that gives me the distance A from here to here. And then same thing with B. It went all the way to 20 centimeters, which is 0.20 minus the 0.08, that's 0.12. And before I use the integral here, I need the force. So I found the bounds, I need the force. We told you by Hooke's law, the force is proportional to the distance traveled. So in this case, the force is given to us as 30 newtons equals k times x. The distance is 0.06. Why? Because it went from the 14 to 20. 14 to 20. That's the distance that was traveled by the spring, which is 0.06. In this case, if you solve for k by dividing, you get 500. Then that will give you what the force is. So the force f of x would be 500x. If you put that into the integral from a to b, a 0.06 and b 0.12, 500x dx, and I know you can integrate that, that will give us 2.7j. 2.7j.